Hello, this is Discrete Maths, MATH1081. We're looking at some questions, selection of problems out of Chapter 4. And so this one I was going to do question 14. Question 14 is using a very simple idea known as the pigeonhole principle, sometimes called Dirichlet's box principle. Was first probably used well before Dirichlet, but he used it in various problems, and his name has come to be attached to it. We will generally refer to it as the pigeonhole principle. And it's a very simple idea. It says, for example, if you've got 12 pigeons and you've only got 10 pigeonholes, then at least 2 pigeons have to end up in the same pigeonhole. In other words, if you start out with M pigeons, which is an M bigger than N, which is the number of pigeonholes, then at least 2 pigeons have to end up in the same pigeonhole. It's a very nice idea of a nice piece of mathematics where you take a very simple concept, this idea of putting pigeons in pigeonholes, and you can use it to prove quite sophisticated number theoretic and other problems and combinatorial type problems. This one here is a fairly straightforward, easy one to do. So it says you've got a 3 centimetre square, and so let me draw up the 3 centimetre square. So there's the 3 centimetre square. And you imagine you're tossing darts at this square, and you've got 10 darts. So think of the 10 points. So you pick 10 points inside here, think of 10 darts being shoved there, and you've got to show that at least 2 of the points, the distance between them is less or equal to √2 centimetres. So, in order to use the pigeonhole principle, whenever you're applying that concept, you need to work out what your pigeons are and what your pigeonholes are going to be. So my 10 darts, they're going my 10 points, the 10 darts, the 10 points, they will be, I'll think of those as my pigeons, and I need to get pigeonholes. So I need less than 10 pigeonholes to try and put them into. Well, once you see 3 and 3 centimetres square, I think you're immediately tempted to divide up this into 9 little 1 centimetre squares. So I'm going to divide this up into 1 centimetre squares, and you've got 9 of them. So let me write down what I'm doing as I go. So in order to give a solution, I'm going to divide the square into 9 1 centimetre squares. And so these are going to be my pigeonholes, and there are my 10 pigeons. So by the pigeonhole principle, which we often just abbreviate to P.H.P, by the pigeonhole principle, at least 2 points lie in the same square. So if I toss my 10 darts at this dartboard, at least 2 of them are going to have to lie in, or possibly on the edge of, doesn't matter. So all I've got to do then is say, well, what's the biggest distance they can be apart? Well, if you've got 2 of them, suppose they land in this square here, then the furthest apart they can be might be at those 2 extreme points here. But I can measure the distance across here, and that's going to be the square root of 2 by Pythagoras' theorem. So that's going to be 1 and 1, and I'll get √2 by Pythagoras' theorem. So again, put some English in now to explain what we're doing. The maximum distance between 2 points in the same square is √2 by Pythagoras' theorem. so the result follows. So at least 2 points have to lie in the same square by the pigeonhole principle, and we've shown here the biggest distance they can be is √2 centimetres apart, and that's what we were asked to show.